Good. And so then I guess I need to share the screen. That works, and then I'll start. Yeah, so good. So now I should be on Amazon. Yeah, so basically, come on, yeah. Basically, what I have is 6 different topics I could talk about, 5 or 6. They're historical pieces I've done myself mostly, but a few of them are with co-authors as well. And they're kind of eclectic. There's no logic. If I get interested in something, I just keep at it. And the beauty of it is, Terry told me when I was when you were growing up, he said, when you have grown up, we'll bring you into the back of the library and show you the biometrical fights between Pearson and Fisher and all that. And I think, anytime you forbid people and say it's behind locked doors, that's why I think got interested in history with myself, which was Terry telling me, when you guys are grown up, as if you ever want to say that to your kids, it's a sure sign that they'll get interested anyway. Yeah, so the very first one is, I think, was the most fun, because that we unearthed data there in London that had been put away by Francis Galton in 1886 and had never seen the light of day since then. And it's the beginning of the regression story, because Francis Galton is the one. I'm sorry, I'll have to apologize for all of those who feel it's sensitive that I'm talking about him, but the fact is that he's the one who gave us the word regression. Very few people know that. So I'll show you that a little bit. Then the other one was for 2008. Well, that was our own Irish celebration in Dublin, when it was the 100th anniversary of the student paper on the error of the mean, right? The fact that he had to alter the T distribution for the degrees of freedom down from the normal, which they'd been using up until then. And what's most interesting to the story on that is that he did it. His math wasn't very good. He had only 1 year of maths and 2 years of chemistry in Oxford. And so he had to do simulations, a lot of simulations, to work out where he was stuck. Once he got to the distribution of y bar and s, he was fine. He could do the transformations then that we still do today to get you from y bar s bivariate to integrate out one of them, and you'll be left with t. But it was the s, the distribution of s or s squared, that he had to guess at. He didn't know that it was a gamma or a chi-square. And so he did simulation and matched up 4 moments and guessed that it must have been, so it helped him with the math, that it was a gamma, and then he figured it out. So his simulations actually then were a test for him as well, that his model fitted fairly well. So very interesting to see how people use simulations back then. Yeah, so that's that one. This one I won't spend a lot of time on, but it's on the website. But it was mainly, I was interested in the hazard function, where it came to be, and then the force of mortality, which is the same thing for the actuaries and so on. But the main idea here being that in actuarial stuff, it took them a long time when you have the age-specific mortality rates, the M's, they call them, anyway, then the actuary rate. The M's were all rows, one after the other, age 1, 0 to 1, 1 to 2, 2 to 3, there were steps, and there was no continuity to it. So it meant you had to multiply things every time you had to get a problem, a product, you had to multiply a whole lot of things. He said, surely it's smooth. And he did a smooth function, not completely clean, but in segments, to the mortality function. And that saved the actuaries days of work. Instead of multiplying whatever, they could integrate a smooth function and get an answer in half a day. So it was major, the idea of a continuous hazard function or a continuous, and that's 1825. And the actuaries didn't accept it right away at all. Some of them still do it the old-fashioned way. I mean, it's amazing. They look to me very old-fashioned today in what they're doing. But anyway, that's that. This one then was an offshoot of that. These two are interesting. Now, Michael, this is not the lottery we wrote about. This is a much more serious lottery. You get called up for this, you went to Vietnam, or you went to the Second World War or the First World War. And you'll see that one I'll spend some time on, and this one is kind of my favorite distribution, so I'll spend time on those. But I'll do a little bit on the first two, just whatever. Just the main thing is I'll tell you where my website is. To be on the recording, I'll send you the PDF of the whole presentation so people can poke along through it later for the bits they want. And one of the things I say here is that I can't cover all these in detail here, so that I feel like you guys have been in cities where they have hop on, hop off buses. Huh? Right, some of you been a hop on, hop on. I'm going to do the hop on bus first, where we'll just go around the city, and we might have time to come back and stop at a few of them in some detail, but I kind of doubt it. I don't know. That's why I was asking Tony how much time there is, but anyway. So the main thing on the first one with Galton is, why can I take this out of the way? I get, know what I can do with it. Do that anyway. Yeah, I give the whole story on the webpage. What I do is when I have a topic I'm working at the end, I put it all in one webpage, so it's one-stop shop. So on that webpage there, which you can link to, I could now if I want, but you can link to that, and it'll start you telling why Galton, to get data for fitting his first regression line, wanted real data. He had data from plants, from peas, and he found that there was this regression where if your parents, as a group, if you take a group of children whose parents were 3 standard deviations above the mean in height, right? So very extreme parents, very extreme height, 3 standard deviations above. On average, their children would only be 2 standard deviations above their generation. So that's what he means by regression. You're coming into the mean, right? So there was a slope, or what do you call it, reduction, dilution, whatever, down, and it was a factor of 2/3 or 3/4. That's what he was looking for. So he crowdsourced the data, because the medical people he wanted the medical people to collect the data from, they wouldn't. I don't think they're great yet at that. So he crowdsourced and paid for £500 for a data set that allowed him to do that. And he had the data in 4 months, and he gave out the prizes and everything. So we wrote about this thing when we found the data, and I'll explain a little bit why we went looking for it. And then we have the raw data now, but I'll explain to you why here we had to do this. Yeah, so there's the first regression line. It's not a 45-degree line like it should be if you regress children on parents. It's only about 3/4 or 2/3. And it's still a mystery to me kind of why this happens and how the world keeps going, because it's, well, there's a lot of things. But the biggest thing is that when he published the data, the way you processed data in those times, you didn't have an Excel sheet and you put all the columns in for every family or every tribe. You took out the couple of columns you wanted. And the most important thing is, instead of doing anything with means and whatever, you made tables of the frequency tables like this. So this is the heights of the parents, and this is the height of the children. When we were working here, you learned how to bin your data, have fewer calculations. If you're doing anything else with correlation there or anything like that, you have to work with too much. You don't do individual sum xi, yi. You did the sum of the mean x, what do you call it? The middle x times the middle y times the number. So it was a lot less work. So that's why he did that. So this is the reduction he made immediately. And you can see from the back here, there's a bivariate normal there. And that's what he spotted. He got some mathematicians to have it. But the weird thing was, he had about 900 offspring from 200 parents. He made the average of the 2 parents as his x. His y was the height of the tribe. But now you have men, children, and female children. And so how are you going to handle the fact that the men would be about 5 inches taller than the women? And today, I guess if you gave this in the class, Michael, they'd say, put male, female in as a dummy variable or something like that. So that's how they do. But there was no regression there. He was before regression. So what he did is something very clever. All female heights have been multiplied by 1.08. So he immediately unisexed the children. Follow me? So you're going to be 1.08 higher than you are, and now you're interchangeable with the others in the row. It was, I thought, beautiful. But in fact, it's better, I think, and it produces homoscedasticity. Whereas if you keep the sexes separate, you actually are violating all the things that tell us about the first course, right? That the standard deviations of heights in men are about 1.08 higher than in the women. So Yeah. The older I get, the fewer examples there are of the linear model with the cohort scale. I mean, it's a joke to think that there is cohort scale, that's just the inner regression. Yeah, so that's what he did. So we felt, well, I want to find them. Stephen Stigler, the historian, he said they're still in, he was a pack rat, they're still in London. So we went and found them. He had collected them in these albums. And then when he was finished his analysis, he wrote out his data set on 8 pages. And that's his listing of the raw data. It says that's all you need. Everyone should put away their data in a manuscript library so that somebody else could rework it later on. Yeah. So here you have, and this would be like, Michael, you're still a stats person, right? Yeah. This would be like sort the heights by family first, by father and mother, and he had the father and mother average. So you could see here, you can't. I'll read it to you. This is a 7'6". What's that? 78 inches. Yeah, 7'6". Yeah. That's 78 inches. 6'6". A 6'6" mother and a 5'7". Father, 5'7" mother, and these are their children. And then they go down in order. Then, so the shortest one is over here. He has them sorted already. He has the kids sorted along as well. And so he can do everything from just by paper. Yeah. So that's why, in fact, if you look at his data and his table, he has in the table, he has the parents on the y-axis and the children on the x-axis. That is weird. Why would you have the parents on the y-axis? Well, it's because that's how he saw it, and he left it like. So you didn't fool around and recreate and reshape or do anything with data in those days. If you put it out that way, that's what he worked from in his analysis. And then he made bins of them going that way. So never redid anything twice. Yeah, so it's quite impressive. So we found these data. Now we can instead of you saying we can take them apart now. We can get your own height back. See now at this point. Right? So that's what we did. And we have put that on the website. It turns out whether you did the additive model or the multiplicative model doesn't make any great difference because it's an awful lot of noise in these data. They were self-reported. They weren't even measured in a lot of cases, the women in particular. So there's a very poor quality of measurement in the women. So the correlation between the father and the son is 0.4. The correlation between the woman and the daughter, the mother and the daughter is only 0.3 because of the slot. And people are always amazed at that today. And I said, well, that's measurement error. Measurement error attenuates correlations and slopes. Right? So here we have it. But students think, oh, you know your height exactly. But your great-grandmother wouldn't have known her height exactly. Worse than that, your great-grandmother didn't report the data, probably your great-grandfather. So how much does he know? He guessed. Whereas the fathers would have been in the army and measured and so on like that. So that's the end of that. So there's the line in the original paper. But what I love about this, he was a very modern man. I don't care what God people say about God. Very modern man. But he did today, but I think of as he made the app. You know, today you make a package, right? You make a package when you produce something today, right? For an R package. Well, he has an app. And the app is a mechanical app. I mean, it's very easy. You could do it by in your head. But if you put in the mother's height and the father's height, and you pull some levers, you will get a prediction for what the child's height is. But that prediction is still used by pediatricians today. If you have a child that the pediatrician is worried about as to whether they're going to go too tall or not tall enough, they can use the parent's height as a first prediction. And then after a couple of years, they can revise that and add in the child's growth at the same time. So we're not that far ahead. Even the genetics haven't added anything to the R-squared for predicting heights of people. You still use the two parents' height, or maybe all the family's heights. So it's kind of nice. These are my own kids. You saw three of them in the picture, right? I don't know how the regression to the mean is working well there or not, because it's about if you have, what is it? If I was three standard deviations below, the kids would only be 2. Anyway, I know how it's working, but I cheated a bit and don't do what I say, or do what I say, don't do what I do. I figured I would alter things a little bit here. So yeah, so that's that. Yeah, so that's that one. The student one, other than the simulations, I won't spend a lot of time on that because I want to get to the others. But this is a long story as well. Everybody thinks this was his first paper. This is actually his second paper. I'll come back to his first paper later on. But he also used raw data, not for simulation. What am I thinking? I have the two guys mixed up. This is the guy who did the simulation. Galton didn't need to do any simulation. Yeah, I said this, right? Yeah, that's it. That's the guy. Yeah, you see, he got this part. This is the key thing. If you can get to the PDF, joint PDF of the two, the rest you're home free. That was crazy algebra retransformation you have to do to integrate out, right? But this is the one that gave him trouble. He turned out to be right. Oh, you also, I think you have to have normality, so then you need independence between that and that for the T as well. That's another piece. The thing has to factor independence. If Gossip's proof is wrong in that case, but the answer is correct, but the proof is wrong. So we have all that in the paper. Then this is the part that was the most fun. We found these, and I'll show you these. The simulations he wrote down, and he did the simulation not with a random number simulator, which we probably do today, or norm, right? We don't use R norm. He took 3,000 criminals. He had their X and their Y. He was doing X bar, Y bar, and the correlation. So he did two papers at once. One on the probable error of the mean or the standard error of the mean, and the other was the standard error of the correlation. So he's kind of doing two jobs at the same time on the same data. But you can see here that he, the simulation. Let's see. I'll go through this very fast here, but these are the notebooks. Where's the simulation? Yeah. So the simulation he did where are the criminals? These are the 3,000 criminals that he got from Scotland Yard. That's a very interesting computer science story about itself, how you store multi-dimensional data about criminals so you can retrieve and identify them fast. You know, it's like a card catalog system. How do you index the card catalog so you can find people quick? It's like in the old days of the books, you could actually by author, by title, by this, and you have to pick one primary one, and they can be secondary and third source. And it's what do you call it? It's not discriminant analysis, but the other one. Principal components problem. So you have to find the component that people are the most different on. Then the second is the orthogonal one to that, the third one. He used this, which is heights of people, I think, along the y-axis there at the top axis, and then one of their fingers lengths is another thing the police wrote down. And then he had a bivariate normal from that, and it's pretty close to bivariate. He has 3,000 individuals. He made 300 individual pieces of cardboard, where he wrote out them, put them in a bag, shuttled them, and then 12 samples of 4, because he was doing N of 4. He had a Y bar based on 4 minus mu, he knew mu, over S of the 4, the standard deviation of the 4, divided by the root of 4. That was his key description. And so he did that and checked out that all the theory worked out. But so it was really nice simulation, but simulation was based on real data to start with, which he had to assure himself were normal to begin with, or bivariate normal. So, and very interesting things when things went wrong, but anyway, you have all the rest of the story here. Yeah, what was the most fun? In Dublin in 2008, I met a guy who had been to Guinness and was looking for the student papers. And he said, no, the student papers are not in Guinness. They're over with Pearson's papers, because he was friends with Pearson. Pearson brought them to London. When Gossett left Guinness in 1935, I think, 36, he went over to be a head brewer in London. Guinness opened a brewery in London in 1936. Pearson was worried that the statistics work would get lost in Guinness, so he came over. Carl Pearson came over and brought students' work, all the materials, so it's in the Pearson archive. And what is so neat, Zilia said to me, this guy, economist, said, did you look at the names of the books? This book is from his original small sample data and notes. That's the one we're talking about. the y bar with 4 over S. This is Hemat's cytometer paper. This is the one I'm going to talk about at the end. It's the boson distribution, where he's looking at how many yeast cells there would be in a field when you look under the microscope. He really discovered the boson distribution. So this is his first paper, 1907. This is his second paper. Can you read the writing there? Eason and Company, where I got my books, in Patrick Street, and Dublin had are they still around? They're gone. They're still around. At the time, they were selling notebooks for science students. The student science notebook. So Ziliak is convinced that that's why student called himself student when he had to get a pen name in Guinness. Is that I don't know, but it makes good sense, right? It's better than the other X-ray. And this is his first paper as well. If this is the second paper, this wouldn't work because both of them are published under the name student. So thanks to the economist in Chicago, I thought this was kind of neat. So I was in the archives in London, found these myself. Yeah, these are kind of neat. But he told me where to go. Yeah, this is Gossett, and these are then the he wrote down his simulation. So every one of these is a sample of size 4. This is the column and this is the row because he was doing two things at once. He was not just doing X bar and Y bar, he was doing the X, Y bar cross product, the correlations. So all of these are in 4s. But if we looked at the book, we'd never know what it was. Right? But it says small sample data. So it's amazing to me. Yeah. Yeah. And then we wrote this up and others. There's a few more things as well. Oh yeah, I was going to come to the computer. That's the rucksack. Top, whatever you call it, the laptop, not the laptop, the rucksack computer that he had that was about 15 or 18 pounds. We had one of these here in the department when I joined. It was a Brunswick. And then we got electric ones and a few others. But he could take this in his rucksack. And it meant he could go home and do computing. Poor Fisher, who was a few years later than him, Fisher wrote to Gossett one time, what computer should I get? Should I get a Mac or a PC? And this guy said to him, get this. You'll get much more out of it. But if Fisher was in Rothamsted at the time, Fisher bought the desktop version, which required electricity. This weighs 50 pounds. I did probably could do more things, but he had to leave it there at night. There was no bringing this home, right? So yeah, so this is the electric version that Fisher used, and you see there's the classic picture of when Fisher, the classic picture of Fisher on a computer is on the Brunswick and Carl Pearson as well, but this was the office version, and so student had to finish a lot of the tables for him. He actually had to finish tables for him. All right, I can't do a lot on it. I'd love to, but I think I want to get to the other two. This is the idea of, what did people think? How did you explain what the force of mortality was and why should it go off and so on? And so it's kind of a long story. I think I leave it for you to look at yourself. There's a few videos. It's too long. I think I would rather leave it. Yeah, as much as I could give a whole talk on that, and I have. So I'll let you find that yourself. It's kind of weird stuff. But it did get interesting later on when the people at GRSS found this, and then the guy at Significance that was there a couple of editors before, he saw Liz giving a talk on this stuff. And a lot of it had to do with funny things about life being a bridge that you had to cross and get to the other end. And every arch on the bridge was 1 year of your life. So it is the conditional idea of going conditionally from 0 to 1, conditional and getting to year 2 or so on. Do you regard them as poetically as crossing a bridge and getting as many arches on the bridge as you could? And then Pearson took up that analogy, and a lot of it had to do with the idea of belief in randomness versus systematic variation, and the idea of laws for probability, whereas you can't deal with the individual, the law for the aggregate is very smooth and stuff like that. So then he asked us to write something extra, and it was right around the time that I think H1N1 was coming in. One of the epidemics was coming around 2000 and that. And we try to connect back then to what people thought about the laws of mortality and so on like that. But in there, we have, I don't know if I have it. Yeah, here we have it. Here we have the idea of excess mortality. You could subtract the deaths from 1 year from the ones the year before, and you have excess mortality. We didn't brand it. We didn't call it excess mortality. We could. We'd have been, everyone in COVID would be saying, was what we, but yeah, it's an old idea. But subtracting all-cause mortality from 1 year to the next was what people used during the epidemic for working out excess mortality. The Irish were ahead of the game here, I remember, because they had RIP.ie. You know that site? You guys were up to date within a day, practically. And I think your health minister was using RIP.ie, or indirectly through the computer science, those statisticians around it. But we tested this out, and it works very well for things like the Spanish flu and other flu epidemics. This is the excess. If you just do the year and subtract it. And because there's no cause of death called Spanish flu. That was the point. So anyway, couldn't get anybody interested in that in 2010. My God, were they interested in this in 2020? Yeah. So we left it. Yeah. So the last two then. Oh, okay, I think we'll be okay. The last two have to do with this. One is to do with lotteries. Why did I get interested in this? Well, I think partly because I went to Canada in 1969, and just that fall, they were doing one of the first lotteries for Vietnam, for the young people of the United States to go, be called up to go to Vietnam. And they have a system, an order in which they were called up. Hard to think of now, hard for you guys to think of that, but that's what it was. And it was very scary for Irish students. I deliberately tried to stay in Canada rather than the US, because there was a kind of a myth, actually, that the Irish students going to the US would be drafted. It never happened, and they weren't. But I said, I'm going to Canada anyway. I didn't want to take a chance. I turned down a job in the US, position in the US. So I remember the American students at the time being very interested in this lottery, shall I say. But the idea of using a lottery as a way of fairness, democracy kind of thing, to call up soldiers is a big deal in the US. Because back the First World War, they had 3 lotteries. And you all have the idea of rank, serial number, all that. Every American soldier got a serial number. Right? And I'll explain in a minute how it worked. But 10 million registered on one day in the United States for the first draft lottery. And then how it worked was you registered locally. So let's say there were 10,000 registered in the Cork office. Those then would get the numbers 1 to 10,000, but given out in a shuffled order. So it didn't matter whether you were first in line or last in line. There were 10,000 numbers, they were shuffled, and then each number was given to a person, and then they posted the 10,000 names up on the post office or whatever, a public place. So Michael, your number is 7342, and that's it. And everybody knew that. So there was no escaping or no anything like that. So what they needed then, so there's a randomization locally for every local center. Some centers were small, some centers were big. The biggest center was about 10,000. So they put in Washington then, they put 10,000 numbers in the drum and drew them out in a certain order. And that was the order to be followed then. So if you were 7,400, if that was called first, you were first up along with all the other people with that number in other sites. That's how it worked. So very, very interesting system. Yeah. And it is hard to believe. There's no way today you'd want to do this with a random number generator. You had to do it physically so people could see it was there. Right? You had to do it that way. So they put 10,000 numbers into a drum. They wrote the numbers on a tiny piece of paper, put them into a gelatin capsule. It was gelatin covering, so you couldn't see the number inside. 10,000 numbers in a drum, and called them out one by one, and it took them 60, and wrote about the board so that were recorded. Took them 16 hours. And you'll see them in how well they did or how poor they did. There was a small draft the next year because they would only get the next group of people in the next cohort. Right, there was only a small little sub because this would have been several, one cohort here. And then this was very big. Is this the one? September, yeah. This is the one in 1918. This one was never used because the armistice came in November of 1918, so they never actually used. And I haven't been able to find the data for this. I have the data for these, but the raw data. This one I can't find. The newspapers had bits of it, but I can't recreate it all. So this took 18 hours. This is the biggest ever. Then comes 1940. So that was Wilson, I think, was the president. This is Roosevelt, FDR. And the war was coming, and they saw this ahead of time. And their first draft was in October of 1940, I think. Yeah. Then a small one, the next year, another big one. So you'll see how well they did. And then the third set you're going to see is the Vietnam, which is a completely different system. Have any of you taught with using the Vietnam data? There's a data set around in most of the textbooks. So that data set from Vietnam is around because it's based on birthdays. These are all based on serial numbers. Right? The birthdays is much simpler, but didn't work all that well. So I'm going to test you as I'll explain in a minute why radiologists, why I'm going to call you radiologists, how random you are, how good you are. It's easy to do this one because I can make this is only 1,200 numbers. So this is the order in which they're drawn, and this is the number 1 to 1,200. So they should be random. But what does random mean? Well, whatever. 1917. What's your verdict on those two? This was a monster. This one's the one that took 17 or 18 hours. This probably took an hour. No, nothing obviously wrong.
But it's clustering.
Are you sure? Well, it's a great data set for testing clustering now. Because our eyes always think we're finding clusters, right? So if you're going to test for clustering here, you better have a good statistic that what's the word? That recognizes that you're looking for clusters. There are scan statistics now that they use for when cancer is uniform and across the area and so on. You have to use the maximum of the worst case and so on, and do that. Looking for clusters is a nasty business. Because people always find the maximum, then they'll draw around a line around the maximum deviation, and then say, oh, look, there's a cluster of cancer. So you have to be very, very careful as to what test you. But yeah, it's too hard. You can't do this properly, but we did a proper test on it. And this, by the way, Mike, talking about our lottery case, this is very close to the Poisson distribution, the number inside of each one. Yeah, so let me see if I have that. Yeah, so here are the formal tests then. Well, it's very hard doing just your eye, but if you just do conditional means here, you just do slices, right? You slice vertically, and you just take the Y bar in each slice and plot them, or make a box plot or anything you want. That's what you get in this case. So it doesn't look too bad. The same in the other one, right? They're obviously a bit more random because it's smaller data set. You have this simple eye, I think, but you can't do it without the smoothing. That's the main thing I learned. And that's what Moore and McCabe said in their book. Testing anything until you can see smoothing, you have to smooth first. And then we did this goodness of fit test where we looked at how many inside of the cell versus a Poisson kind of a thing, or a simulated version of it, and you get very close to observed and expected. That's how often the cell would have 5 and 4 and 3 and the same. And everything looks very good. So the 17-18 lotteries, the first two looked like they were really, really good. Wouldn't you say? Yeah, I mean, every way you test them, we did all sorts of things, and they look fine. But this is the first time these data have ever seen the light of day. I had to go scour a lot of newspapers, go down to Washington, the archives, find these. But they are public. They were very public about it because these numbers appeared in the newspapers, and this is what determined, and everyone knew what was going on. Now, This is 1940, 41, 42. Is it? Yeah. Anyway, sorry, I know I can get rid of this thing. Okay. You don't need anything fancy here to know what the hell's going on here. Some serious problems. And yet, this was found, this anomaly was found by a statistics student in the University of Chicago about 3 days after the blockage. And his professor, they wrote it up in the Chicago Times or whatever it was, the Chicago Tribune. Very little fuss. Very little fuss. Wait to hear what happened in Vietnam. Major fuss. But no fussing here, and I'll explain why. But here, yeah, here's the formal test. Okay, okay. Well, of course, when it went wrong this time, they went all sorts of lengths to mix them more and more. They were throwing them up. They had a big blanket and they were throwing them up in the air. They went hours making sure they were well mixed on the way in. But here, obviously, what's your impression here? What went wrong before we start? Kind of hard to tell.
They're going to do with the number of digits.
No, they were all 4 digits, I guess.
Well, except for 1 to 1,000.
Oh, yeah, no.
1 to 999.
I said, but it goes well out to,
It goes well beyond that.
it goes well out to there, but maybe, yeah. Yeah.
There'll also been horizontal bands.
Yeah. And then it seems to be getting better after a while, right? Seems to get better after a while. When you actually see the Americans on this one use the same drum that they used in 1917. They're big on ceremony. Have we got any American born people here? No, they're big on ceremony. So they had the ribbons and the piece of fabric and things. And these drums are still in Philadelphia. They're kind of national icon. The drums used for the lottery. And Roosevelt used it again then in 1940. They had 17,000 fit in the drum the first time. This time they had only what? 9,000 to put in the drum. But they were bigger. They were bigger. The guys hadn't calculated right. The tablet, the capsules were bigger. And they overflowed the drum. So this is Roosevelt drawing out, reading out the numbers as they were called out by the Secretary of War. This is the original drum. It was too small. They put a collar on it, and they put the collar on in the inside. So the collar goes down through here and ends here. It ends here. There is no way that I think from here can get pulled out there, and there's no way to mix them. So they're a big problem. And I think these were probably put in without much sorting at the beginning. So let's put all the numbers 1 to 100, Michael. That's probably what you're saying, right?
First third or so.
Yeah.
They can't be picked.
And then apparently what happened is once they got out of this much done, they took off the thing, the collar, and now we had a little bit more mixing. And you can almost see here where they took off the collar, right? Yeah, by a third of the way through or something like that. Yeah, so this is a major disaster. Again, major disaster. I mean, this is about as bad as it gets. There wasn't a peep out of people. Nobody could, I mean, there was a national fervor about the war anyway. But I'll explain in a minute why it is that it's no big deal, even though it looks very unfair. All right, now we come up to my time now. 1969, I was in Waterloo at that time. And this one was on television. The others were public events too. That was the other thing. There were probably very public events. People were listening on the radio. This was on television. I watched it in 1969. There were American students there worried about their draft. But Nixon had said, look, let's be fair to everyone. Let's tell people ahead of time kind of when to expect so they can plan their lives and go to graduate school, get on with their lives. And he also didn't like the idea. He didn't like the idea of age. There was funny things going on about the age when there were titles on. He said, let's make it nice and simple and let everyone know ahead of time. And they switched to birthdays. Instead of your serial number, you were identified with your birthday, but also they have your nephew at the same birthday. So it's not a person, but it should be much easier to do now. You want 365 birthdays in the year, or 366, depending on which year it is. And so you would think that's no big deal. But I think they were so nonchalant about it that the weekend before, 2 army generals did in their home. got the thing late the weekend before. And didn't think much about it at all. They didn't want to stir them because they might break the capsule. They used the same thing of putting the number inside and covering it up so it would be unfair. But they didn't put a lot of it in. So now, let me ask you, with your eyes now, if you see any non-randomness anywhere in any one of these? Pretty hard to tell, isn't it? They all look good. Do they all look good to everybody? If there's a major disaster. Let's see if my. Have you got friends as radiologists? Anybody in the family radiologist?
No, I don't know any either, thankfully. Is it pretty around 1969? Does it look like the earlier in the year you were born, the late, the quicker you're thrown out? I'm looking at this.
Which, so that what correlation would it be? Positive and negative correlation?
Positive. This is positive.
You see a positive one. Well, I've given this to every class that I've ever taught. And nobody has ever, even after warning that there's one of these that most people don't get it, yeah. But it is the 69 one that happened. So let's look at the 69 one, see if it's it.
It's much less than the top right.
There you go, there, much less. So listen to what the wife said about the radiologist. The year that I was teaching, 1 year, I had a radiologist from Australia. And they're used to looking at kidneys and see if the kidneys filling and, they're looking at these things where they see it. He said, he didn't say it that way. He said, there's a defect in the upper right quadrant. There's a defect in the upper right. Is that what you were saying, Michael?
No, I was seeing something in the left.
Well, the excess is probably there, or you see the excess. He said there's a defect in the upper left quadrant. So that is amazing. I really now respect radiologists. They're not guessing anymore. Yeah, it was quite something. Yeah, exactly. And so this was caught very quickly as well. But you have to smooth. You either have to do something. So in Moore and McCabe's book, they use this one. And I think they do it in like 12-month or like 30-day bands or 30 number bands. And they do a median, a running median or something, and you can see it very clearly. When I do it, let's see what I do. Yeah, so you see, there the conditional. So Michael, the ones drawn first were from later in the year. Yeah, and the ones down there, they were lower down. So there's a cartoon in Moore and McCabe's book. They won controversy. It's a really good book it's not very technical, it's a very good book about issues and controversies and statistics. It's about preventing dating nice things. It's kind of a Spiegelhalter kind of a book. And he has a cartoon of the two guys out in the jungle in Vietnam. And one guy says, oh, you were born in December too, as well. The two of them are. Yeah, the December guys got born. Yeah. And the reason for it, this is the dumb part. They had only put 360 bees in a drum. And they were so sloppy. Let's get all the January ones done. They did those. Put them in the drum. The February, the March, April. They didn't even mix. The first guy that they put them in that big bowl, I think. Looks like the same bowl. There's a picture of the guy trying to reach the thing. His arm isn't even long enough to reach the bottom of the bowl. So he picks right from the December ones that get in first. He didn't do much, picking around. I mean, so next year, oh my God, you should see what happened then. The next year, there was a double system and a triple system. Yeah, this is the double system they used the next year. We had a double randomization. We're randomizing the order and we're randomizing the balls. There's two sets of randomizations happened even before they go into the drum. So that, they went wild. Yeah, trying to get it right. So there was absolutely no way. Yeah, and indeed it worked, because if you look at the second one, absolutely exactly here and absolutely. So what I call this system here, sort of a double robustness. And I think it's the same idea why there was no problem in 1940. If you think of it, you saw and your relatives saw and every your friend saw all the numbers going up on the post office. So, and that was fair. Everyone saw it as fair. And the second one in Washington hardly mattered. And I say you could have called them out 1, 2, 3 in Washington, it would still be kind of fair. Because my understanding, is there any, you guys do causal inference over here? They do in my place, but I don't believe in it. I mean, I don't believe it, but I think it's a lot of extra stuff or nothing. But they have this thing called double robustness for some of their models. Have you heard of it? Double robustness means you have a model for the treatment, I think that whether you get the treatment or not, it's to try and make things more experimental when they're non-experimental. So they model the probability that you get a treatment as a function of the covariance. And you have to have a model for that, statistical variance. And then there's another model going from the treatment to the outcome. And apparently all you need is one of the two models to be right, and you copy. So that's what I naively think of as the what do you call it, the double robust. And as long as one of the two works, you're okay. And that's kind of the principle here. As long as one randomization works or the other, you have two, so you're covered. That's the idea.
Jimmy, did they develop February 29th in 1970?
They did. Yeah, there were 366 one year and three, because it depended on the year you were born. 1952. So I think the first group up were 18, and they're born in 52 or something. So it's the year you're born. They had to worry about the birthday the year you were born. Right? So I think the first one was only people born in 1950. Was 52 would have been that would have been a leap year, right?
Yeah, but then 56 would have been, was 366 in that as well.
Are there? I think there might have been something extra that the first year there was more people and then there was only new groups. I'll have to look at it. Yeah, I'm sure it's in the paper we've written about it. Yeah, but yeah, they did worry about that. Yeah, exactly. So today, they now have switched also, in that days they did drum, now they have bingo balls. And they're ready in case the US will ever call up its troops again. They don't have to at the moment, but if they ever did, they have these and they bring them out every year and dust them off. But they're ready, you see, and now they have but there's a very long protocol for the order in which these are put in the drum. You see, so there's a whole lot of robustness built in. So that's it. So I'm at 3 o'clock. How much tolerance do people have? You're very tolerant. Leave if you want to. If you have to go, I'll do another 5 or 8 on the last one, which is a possum, because there you actually have to work a bit as well with your eyes. So this is the one that kept me sane during COVID. I'd always been interested in the possum distribution, and I'm wondering about the history. It turned out possum should never have had his name on the possum. He did nothing except take the limiting case of the binomial, goes to possum. Bear, you agree? Huh?
Entirely.
Yeah, exactly. And so why his name got on it, good luck. I think Boscovich or whatever, one of the guys who wrote the book later, put his name on it. He did nothing. There's a debate between Stigler and a bunch of others who should get the credit. But the two guys who were the first to reinvent it and use it and bring it into the 20th century were the Dublin guy, Goss, the English guy, Gossett, looking at yeast cells under the microscope. And a guy from my university, but we take credit to him, he did a lot of the work for the Nobel Prize in McGill, but he's a New Zealander, Ernest Rutherford, so, father of splitting the atoms. So he was counting atomic scintillation, disintegrations of whatever from the thing. So that was the chemist and the physicist were the two that needed this distribution, and it worked beautifully. And if there's one take-home message, which may get lost if I don't say it now, about the Poisson distribution, that's about the only place the Poisson distribution fits. In real life, the Poisson distribution is way too tight, way too exquisite. It only works in the lab if everything is right. And even Gossett had trouble with the yeast cell where he had deviations from it. So yeah, so this is the long history, but I will give you the 2 parts here to do with our guy here, Gossett. but it goes way back, you see, to the beginning. Very other interesting thing as well, commercially driven, is the guys before 1900. The Austrians, I think, who was the Zeiss company? You know, the Zeiss camera company? They're somewhere in Austria, Germany. Germany, yeah. They invented one of the, what do you call it, the microscope that you could see cells underneath the microscope. So then they had to have some protocols for how many you would need to count in order to get a good concentration. Yeah. And the Poisson distribution comes into the number of these speed and so they were on the ball, and they had the normal approximation for the Poisson already in the 1970s. Yeah. But it took this guy and this guy to use it in real small example cases where they would only be, where if the mean of the Poisson is less than about 10, you can see the skewness. If even below 5, especially, you know, that's where the expectation of 5 for the binomial, the same as Poisson. Once you're about 10 double digits, the Poisson is indistinguishable from the normal. So very cleverly, these guys did tests going down below that where the mean was 3 or 4, and you can see the skewed discrete Poisson distribution instead. So, and then the modern story. So I'll give you this one first. Yeah, just quickly. So this is our guy in Dublin. This is his first paper, and it's a beautiful paper to read. He derives the Poisson from the limiting case again of the binomial, but then he does loads of experimental work where he's doing stuff, and he's actually counting these things himself. So this is my little reenactment of it in the 21st century. This is what it would look like, I think. People would tell me, if you were looking at the microscope and moving the fields along under the microscope, in some cells, in some you'll see 3 and 2 and 1 and so on. And so he did various ones with various lengths, various mu expectations, and show how beautifully it fit the Poisson distribution once he got it. But he was very careful that if you had any clumping or any kind of contamination or things where the cells weren't broken out separately, you got violations of the Poisson right away. You get either way too many big numbers or a lot of zero if there's clumping. So I always give the example of raisins in a bun. You know, if you don't mix the raisins in a bun, in dough, you will get hot spots and cold spots the same way. So this is kind of fun for people to do, but it's kind of boring. Did we make videos of this? Yeah, I think we have videos of this. Or not videos, things like this. Yeah, I mean, it's kind of boring stuff to do, but you can get students to do it, but they won't do much of it. They won't do much of it. Yeah, exactly. But they should. They should be told. I did have one doctor who told me once about something about white blood cell count. I said, how many do you guys have to do it when you're doing manually the medicine? I said, we were told the rule for blood cell counts is how many fields do you count before you do the total? And he said, no, you don't do fields. They tell you you have to count until you reach 200 cells. And then you divide that number of cells by the number of fields you counted, and then you can convert that to concentration. But why would that be? Well, it turns out 200, if you have a mean of expectation around 200, the Poisson standard deviation is square root of that, of 15. 2 15s is 30. So you're off by 30, plus or minus 30 on 200. You're off by 15% on 100. So that's kind of the working rule they used when you had to do it manually yourself. So it kind of checks out. So as counting statistics go, everyone hates doing it because we have to count to 200. I don't care whether you find fewer or lot, we just keep going. So that's how that worked. So anyway, that's I call this one the distribution of events in space. But the distribution of events in time is much more fun. And this is our two guys, Rutherford. He's now in Manchester, and basically looking at atomic alpha particles, I think, or something. They were, but very, very tedious work. Very, very tedious work. Where you're looking into a tube, you're looking through a microscope. At the other end, there's a tube, and at the other end of that, there's radioactive material. And if you go in the dark and you train your eyes to accommodate the dark, you can start to see the flashes through the microscope onto the tube and the back of the tube. And he said the good guys would take 5 minutes break and then 5 minutes counting, 5 minutes break, but after supper when the building was dark. And Rutherford would be checking. And how you count it, there was a paper tape running. The paper tape was running, and every time you saw a flash, you pressed a button and it made a hole in the tape. And so when you were finished, you rolled out the tape, and you could see, and you divided it up in 7.5 second things, and you could count how many there were in every bin in the tape. So it was really tedious, but beautiful work, beautiful, absolutely. And I still have the paper here. You see, just read the paper, and you'll see how beautiful these guys were at writing. Yeah, and then the results, and I must, yeah, and then this is what this is the numbers of bins where there was no count. How many was 1, 2, 3? The mean was about 3.7. So your Poisson distribution here, observed and expected, with that mean. And they're pretty damn good, but it's a lot of care to do, a lot of care. But beautifully done. And then what's also done that was even nicer is this guy, a couple of years later, said, I don't just want to count the numbers and see what the distribution is. I'd like to see the spacing between the events, because he thought you could get more information from the spacings in time than from the count. And the spacing follow an exponential distribution. Is that right? Or yeah, exponential. Which drove them crazy, because one of the things they thought was non-random was the fact that sometimes the flashes would come, a lot of them together. And then there'd be a long wait, you'll see it in a minute, and you say, well, why that doesn't look random to me, because that's boop, 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 and then there'd be a long wait, and then be a few more. I think we have no idea how to do randomness in our head and judge it. So I said, let's do it. So that's what I hope this is working. Yeah, and I'd put you working. We should turn down the light. Well, look, I made it for our students, wouldn't do 5 minutes of counting. That's way too much. I said, let's do a minute. So we'll do a minute of counting. And so I have a bunch of them here. I hope it works. Which one do you want to pick? Pick one of them for us. 0, 5, okay. Oh, and the audio one is even easier to, you'll find in a minute, the video one. Okay. There are the two of them. When it counts down, and it's every 5, you keep counting. Everyone count. Start it down. How many you see? Yeah, exponential, and then 2. That's it. Michael?
Oh, I lost it very early.
See, yeah, it's tough work. They did 5 minutes of this and that. How did you get?
24,
See,
34.
anyone else? See, we can't even agree on the count. Forget the randomness. We can't, there's even problems with that. Yeah, exactly. Yeah, so this is good stuff for people, but you got to keep it small. So I have all these on my website for a thing, and I think it would be good practice for you. But we haven't a clue what random. And it's the exponential is the kind of key that says that's why you see those bursts and then long. Yeah. Anyway, I think that might be near the end. Yes, I wanted to get as far as that. Yeah, the rest, yes, I think so. I think that's it. Yeah, yeah. So I'll give you my website, and I'll give it to Michael. I think that's the best thing, the PDF. most of this is on my website anyway, in various places, but the PDF will show you where to go, I think, on my website. Yeah, so Tony, we're done. Yeah.
Thank you, Jim, for absolutely fascinating. Rather than questions that actually.
Yeah, let's do it outside. You know, on the website, you have all this stuff in, absolutely, and I'll send Michael the recording as well. Huh? Yeah, well, when you might need to do this. At your age, you're not there yet, right?
Not quite.
That's it.
Get it there rapidly. John.
Huh?
Yeah.
Come on, now,
Yeah,
come
I
on.
was surprised I knew Marvin Selling when I was at Harvard, and because he moved the entire.
Yeah.
He was explaining to us.
Yeah, yeah, oh yeah, I was one of the crowd that moved from Buffalo to
How
Boston.
they wanted him to move, to set up the place.
Yeah.
And he moved everybody with him.
Yeah, 12
That was
or
the
12
tradition.
PhDs, I think, yeah. Yeah.
Because they said, I think Harvard was one of the few places to have a biostats department before a stats department. The
Yes.
Stats guys were there.
Stats were unusual, yeah. There's a history of the stat department just written now, 50 years ago.
Oh, yeah.
It's a fun
But
one.
it's funny, what I found weird when I was there is we didn't go near the stats department at all. They were too.
No, that's right, that's right.
There was no intermingling with the.
Oh, no, it was pretty awful, yeah, stuff.
Was that because they were more theoretical?
They were over, no, it was
They were on a
partly
different
that,
campus.
they were another campus across the river. And geography is horrible. It really loses people. Yeah, no, it was.
The stats guys are where you would expect.